Prime numbers present mathematics with a core paradox. They are the indivisible atoms of arithmetic, the building blocks for every other number. Yet at a local, number-to-number level, their distribution appears completely chaotic, fracturing into unpredictable gaps and clusters without any obvious pattern. That local unpredictability baffled mathematicians for centuries. Then, in an 8-page paper published in 1859, the German mathematician Bernhard Riemann moved the study of prime numbers away from basic discrete arithmetic. He translated the problem into the continuous topological realm of complex analysis. This 3D topographical landscape represents what is known as the Riemann zeta function. Riemann discovered that the chaotic sequence of prime numbers is actually governed by this highly complex, continuous geometric surface. Specifically, the primes are controlled by the zeros of this function, these deep plotted dips where the mathematical landscape drops exactly to zero. Riemann realized that mapping the exact locations of these specific dips is the only way to prove that the chaotic sequence of prime numbers secretly possesses a perfectly balanced macroscopic order. This graph maps out that landscape on a 2D complex plane. The Riemann hypothesis makes one highly specific, incredibly bold claim. It asserts that every single non-trivial zero of the zeta function falls exactly on a single stark vertical boundary, called the critical line, where the real coordinate is exactly 1/2. In the year 1900, the mathematician David Hilbert cemented the legendary status of this claim at the International Congress in Paris. He included the Riemann hypothesis in his defining list of the 23 ultimate unsolved mathematical problems. Fast forward to the modern era, and the urgency to solve this mathematical mystery has only intensified across the entire globe. The Clay Mathematics Institute designated it a Millennium Prize problem, offering a $1 million reward for a rigorously peer-reviewed proof. Today, it stands as the undisputed anchor of modern analytic number theory. A proof of the hypothesis validates hundreds of dependent theorems across various mathematical disciplines. Conversely, a disproof necessitates a total restructuring of the field, as the distribution of primes would prove to be significantly more chaotic than current models allow. To see how those zeros control the primes, we look at Riemann's explicit formula. This smooth, upward trending curve represents our expected average count of prime numbers, but the actual primes deviate from this average. The complex zeros act as mathematical error waves, shown here oscillating against the main curve, that constantly correct and refine our estimation. The size of these corrective waves depends entirely on the location of the zeros. If a single counterexample zero exists off that critical line, these error waves inflate exponentially. It would mathematically dictate that the true distribution of prime numbers is significantly more chaotic and biased than our current models predict. Because mathematicians cannot yet prove the hypothesis unconditionally, they rely on zero-density estimates. These are rigorous analytic theorems that place strict upper limits on exactly where any rogue counterexample zeros could theoretically hide in the complex plane. For over 80 years, these estimates were stalled by a mathematical barrier known as the Ingham bottleneck. Then, in May 2024, mathematicians Larry Guth and James Maynard deployed highly advanced Fourier analytic techniques to shatter that barrier, dramatically improving the maximum frequency with which specific mathematical sums, called Dirichlet polynomials, take large values. While their work does not prove the Riemann hypothesis outright, it represents the first substantive foundational improvement to these bounds in over 8 decades. This result shrinks the available mathematical space for counterexamples, forcing any theoretical exceptions to hide in a narrower proximity to the critical line. While theorists push the bounds from above, computational mathematicians are attacking the problem from below. Using extreme high-precision computing, the first 10 trillion non-trivial zeros of the zeta function have been rigorously evaluated. Every single one resides flawlessly on the critical line. Other researchers are exploring an entirely geometric frontier. In 2026, Fields medalist Elaine Kohns utilized the physics-inspired Weil quadratic form, a tool drawn from modern spectral geometry, to calculate remarkably precise approximations of the zeros, mathematically forcing these generated values to lie exactly on the critical line. The hypothesis is also linked to several other problems through the concept of mathematical equivalence. Researchers have identified alternate, elementary formulations, such as Robbins or Lagarius's criteria regarding the sum of divisors, that are logically identical to the original conjecture. This means the entire Riemann hypothesis can be tested through different lenses. Finding just one single, astronomically large integer that breaks a simple inequality regarding its divisors would be sufficient to invalidate the entire 165-year-old framework. The sheer interconnectivity of the problem dictates the terms. It must be flawlessly universally true across the infinite span of numbers, or a single chaotic integer brings down the entire architecture. Proving the generalized Riemann hypothesis, GRH, provides a direct guarantee for computer science. It ensures that checking whether massive numbers are prime can be executed deterministically in polynomial time. This brings us to a highly pervasive, viral internet myth: the assertion that a sudden, valid proof of the Riemann hypothesis would instantaneously break modern asymmetric cryptography, rendering algorithms like RSA totally useless. That is completely false. RSA encryption relies strictly on the computational difficulty of factoring specific individual prime numbers. The Riemann hypothesis merely provides an analytic formula for the average macroscopic distribution of primes. Knowing the overall behavior of the ocean does not give you an algorithm to track a single drop of water. The actual looming existential threat to global encryption is quantum computing, specifically Peter Shor's algorithm. Shor's protocol relies on quantum Fourier transforms and period finding, a mechanism that operates completely independently of the complex zeros of the Riemann zeta function. If a mathematician published a flawless proof of the Riemann hypothesis tomorrow, the negative impact on global cybersecurity would be exactly zero. Our current cryptographic infrastructure already safely assumes the hypothesis is true. Looking ahead, the absolute latest frontier in this pursuit isn't just human ingenuity. It is the rigorous, computer-assisted formalization of the mathematics within the Lean-4 proof assistant. This community-driven software mechanically verifies mathematical arguments at a microscopic axiomatic level. By completely eliminating the possibility of human error or logical gaps, formalization establishes a rigid, unhallucinable finish line for the Clay Millennium Prize. Whether it is finally resolved by a sudden flash of human analytical insight, or by the inescapable, methodical grind of machine-assisted verification, the 165-year pursuit of the Riemann hypothesis has forced humanity to build the most sophisticated logical architecture in history, all just to understand the hidden symmetries of counting.